Hello again, geometry. So last lesson we went into inductive reasoning and there was some vocab in there, and I mentioned how this unit has a lot of vocab. We're going to introduce quite a few more vocab words in this lesson. All right, so and this lesson is kind of the basis for not only the next few lessons, but also proof in general, which is a big part of geometry. So like I said, last lesson we learned about inductive reasoning. The next couple lessons, we're going to look at deductive reasoning. All right. This is the type of reasoning when you start with a general rule and make a specific conclusion. So first big word you need to know, and you will see this word a lot, is a conditional or a conditional statement. Doesn't mean the same thing. Conditional, I'll just shorten it down to conditional, is a statement that can be written in if-then form. If this happens, then this happens. Okay. Symbolically, and I will use this quite a bit, is P arrow Q, and how that's read is if P, then Q. All right. It has two parts. An if-then statement has two parts. Pretty obvious, if and then, but we have a name for both of those parts. The if part is called the hypothesis. And then the then part is called the conclusion. Sorry, not so hard to read. Conclusion is what you're trying to write there. So in the next statement, I want you to identify the hypothesis and conclusion of the conditional statement. If I eat fast food, then I am unhealthy. All right. So I'm not worrying about whether that's a true statement or a false statement right now. Some of you might be like, no, that's not true. That's not what I'm talking about. I want to identify the hypothesis and conclusion. Now, a lot of people say just the first 1, 2, 3, 4, 5 words of the hypothesis. You're almost right. But all I want is I eat fast food. So I eat fast food is my hypothesis. The conclusion then, if that's true, that's a general rule, I eat fast food. The conclusion from that general rule is I am unhealthy. Notice what words I am not circling, right? In the hypothesis, it does not include the word if. And the conclusion does not include the word then. I am kind of a mean one on that. So please make note of that. Now, a lot of you might have, as I first said that first statement, said, oh, that's not true, or yes, that's true. You're talking about the truth value, and that's what we're talking about next. Conditionals do have a truth value. They are either true or false. Okay. To show that a conditional is false, you only need to provide one counterexample. I talked about a counterexample in the previous lesson. Now I'm going to talk about what is a counterexample when we're talking about conditionals. Okay, so a counterexample is an instance or a time when the hypothesis is true and the conclusion is false. Okay, so let's jump right in. If a figure is a quadrilateral, then it is a square. So the hypothesis is a figure is a quadrilateral. So basically the population I'm looking at is all quadrilaterals. All right, so it's got to be a quadrilateral. The conclusion is, well, then it's a square. Well, that's not true because there are other types of quadrilaterals, right? If I'm looking at the general population of the quadrilaterals, I cannot conclude that all of those are squares. So a counterexample to that would be a rectangle. A rectangle is not a square. A trapezoid, a kite, get the idea. I will see some people say triangle here. A triangle doesn't even fit in the population that we're looking at. If we're looking at the population of quadrilaterals, I'm not even looking at triangles right now. So I can't say anything about the conclusion because the hypothesis wasn't true. Hope that makes sense. Another one, if the absolute value of x is greater than 0, then x is greater than 0. So we're looking at the times when the absolute value of a number is greater than 0. Well, that's almost all the time, right? Pretty much every number. The only number that would not be included in that population is 0 itself. So before I do anything with that, is x equals 0 a counterexample? Yes or no? No, it is not. It's because 0 isn't even in the population or the hypothesis. Okay, if I put 0 in for x, it's not a true statement, so the hypothesis would not be true. Therefore, it's not a counterexample, because a counterexample, the hypothesis must be true. All right, so what would be a counterexample? Well, any negative number. Let's just say -5, for example. If I put -5 in for x, the absolute value of -5 is 5, and that is bigger than 0, which is true. So the hypothesis would be true, but x itself was not bigger than 0. Okay. Writing a conditional from a statement. So this is not written in if-then form. We're going to change it to if-then form. So this is an acute angle measures less than 90 degrees. Okay. So we have an acute angle. What does it do? So if I have an acute angle, or if an angle is acute, then what can I say about it? Well, then its measure, or it measures less than 90 degrees. That's changing it into a conditional statement. I'm not going to do that a ton, but thought you should see it. All right, Venn diagrams. A lot of Venn diagrams can be written as conditional statements. So here's a Venn diagram with athletes and Olympians. The conditional that I can write from this is the following. If I'm an Olympian, then I'm an athlete. Okay. So if I'm an Olympian, then I'm an athlete, which means if I'm an Olympian, that means I'm in the blue circle, right? I'm right here. Which means I'm also in the big rectangle, which is the athletes. So if I'm an Olympian, then I have to be also an athlete. Most of us in geometry, if we play a sport, for example, we would fall in this category. We are athletes, but not necessarily Olympians. So it wouldn't even fit in this conditional because we're not even in the Olympian population. If you wanted to look at that and see if there's a counterexample, go to the next Olympics. Everybody that's participating, see if they're an athlete. Well, they are. And so that would be true. It's kind of hard to show that something's true, but yeah. Now we're actually going to draw a Venn diagram, kind of go backwards here. If you live in Chicago, then you live in Illinois. Okay. I'm going to do it wrong here first. I'm going to use the same idea, rectangle and circle. You don't have to do it that way, but let's say Illinois is here. And I'm going to put Chicago here. Is that a true Venn diagram? Hopefully you see that it is not. If you didn't know, Chicago is in Illinois. So Chicago, if I live in Chicago, then I live in Illinois. Well, according to this, that would be false, but the diagram is drawn incorrectly. This is the correct drawing. Chicago would be here, and Illinois would be here. Okay. All right. Stick with me for a little bit longer. Converses. Okay. There are 5 types of conditional statements. The conditional is the first. The original conditional is what you'll hear me say. Converse is the second type. The converse is still a conditional statement, but what it does is it switches the hypothesis and conclusion. Okay. So symbolically, what you'll see written is Q, then P. If Q, then P. So write the converse of each conditional and then determine the truth value of each statement. So I'm going to kind of go in a different order here. I'm going to look at the original statement, which is the conditional. So the conditional is that true or false? So if X equals 9, we're only looking at the time when X equals 9, then X plus 3 equals 12. Well, that's true, right? If we're only looking at when X equals 9, well, then X plus 3 has to equal 12, right? Now the converse, what that does is it switches the two pieces. So if I'm saying that's Q, or sorry, that's P, and that's Q, I'm now going to switch it. If X plus 3 equals 12, then X equals 9. So now let's look at that switched statement. Okay. We're only looking at the times when X plus 3 equals 12. Well, you know your algebra. If I solve that, then X equals 9 every single time. So the truth value is also true. Okay. Next one. Change colors again. If you travel legally from the United States to Kenya, then you have a passport. So the hypothesis is you travel legally from the US to Kenya. The conclusion is you have a passport. Is that true? Yes, it is. If you're traveling legally, then you have to have a passport, especially, well, if you're going international, which Kenya is another nation. So the converse then is if, notice that the converse is the actual statement. The truth value of the converse is true or false. If you have a passport, then you travel legally. I'll run out of room here pretty quickly. From the US to Kenya. Now, truth value of that one. Well, if you have a passport, that's what we're looking at. If you have a passport, a lot of you in this class have a passport. I have a passport. Does that mean that I travel legally from US to Kenya? No, I could go to literally, well, not literally, I could go to many, many other countries with that passport. It does not guarantee that I'm going to travel from the US to Kenya. So the truth value of this is false. Okay. Next one. If a squared equals 25, okay, then a equals 5. This one's a little tricky. The truth value of that is actually false. Why? Well, if a squared equals 25, we're looking at the times when a squared equals 25. Well, there's two times when a squared equals 25. When a equals 5 and when a equals -5. So therefore, I cannot conclude that a equals 5. It could also be a equals -5. So that's the counterexample, right? So a lot of times you'll see me write the counterexample, is right below the false statement. I'm not going to have a counterexample to a true statement. That doesn't make any sense. So what I'm going to do is I'm going to now write the converse. If a equals 5, what can I conclude? Then a squared equals 25. Now that statement is true. I'm only looking at when a is 5. So if a is 5, can I conclude that a squared is 25? Yes, I can, because if I square 5, it's going to equal 25 every single time. All right. Now, I left all these up here because I want you to see this. I'm going to look at truth values now. A lot of people think that if you say a conditional is true, then the converse is true. Well, that was the case here, but it wasn't the case on number 2, right? if the conditional is true, which it was, then the converse is true. Well, it wasn't. So that would, number 2 would be a counterexample to that thought. All right, so some people might say if the conditional is false, then the converse is false. Well, that's not true either. Look at this one. It'd be a counterexample to that statement. So if the conditional is false, which it is, then the conditional is false. No, it's not. This one was true. Okay, so maybe they switch. So if a conditional is true, then the converse is false. Well, that's not true either. Look at that. If the conditional is true, then the converse is false. That's not true. All right. So basically what I'm getting you to look at here is the truth value between a conditional and a converse cannot be determined just by generics. Okay, so if the conditional is true, we can't say really anything about the converse. If the conditional is false, same thing. All right, we'll talk about that more, especially with the next lesson, which involves the next 3 types of conditionals. And that concludes lesson 2.